Terry. I hope you found that spreadsheet exercise to be helpful in terms of understanding and visualizing the way the equilibrium theory of island biogeography works. So in this module, we've covered a fair amount of material, and so to recap, let me point out a few of the key points of things that we've covered. First, the equilibrium theory of island biogeography is really a framework for understanding species richness on islands. And it was popularized by Robert MacArthur and E.O. Wilson. At the core of the equilibrium theory of island biogeography is really a model that again tries to explain patterns of species richness on islands. And when I say islands, I mean any sort of unnatural or natural island, right? So an unnatural island might be one that we've created, a forest patch surrounded by urban and suburban development. But an island could also be a mountaintop. It could be a pond. It could be, in fact, an actual island. The main components of this model include immigration rates, so the rate of species reaching islands and colonizing them, extinction rates, so the extinction of species already residing on that island, as well as area, so the size of an island, and the degree to which that island is isolated. So the equilibrium theory suggests that we can estimate species richness at an equilibrium state if we know something about those characteristics. And an equilibrium state now would be a state in which the number of species, the richness of species, does not change from one time period to the next. It's relatively constant and unchanging over time. So we can predict that using this framework. An important point, though, is that even though richness is unchanged from period to period, that the composition of that community of organisms, that community of species, is in fact changing. So we have this recurring influx of immigrants and this recurring extinction, which causes a lot of turnover in the composition of species. So composition changes. There's a lot of turnover or turnover rates. So the model then allows us to make predictions about the equilibrium state of species richness on an island, given that we know something about immigration and extinctions, and that we know something about area and isolation. And what we see is that areas that are larger, so larger areas, will have higher rates of equilibrium, higher rates of species richness relative to smaller areas. So bigger islands have more species than smaller islands. And we also see that those islands that are much closer to a mainland, so they're less isolated, will also have more species than those that are further away at equilibrium or more isolated. So that's the basic equilibrium model and theory. And really the model and theory have provided a framework for the way conservation biologists have really approached landscape conservation in the last several decades. Now there have been a lot of variations on this basic model since it was really developed, and those variations have been really aimed at incorporating a little bit more biological realism. So what are some of those variations? Well, one is to incorporate non-linear immigration and extinction relationships. So think about the graphs that we've drawn. They've all been linear relationships between the number of species and immigration rates, or the number of species and extinction rates. We were drawing lots of straight lines. But that may not necessarily be the case in a lot of systems. We might have curved relationships, non-linear relationships. So with respect to immigration, a curved relationship might result from a situation in which there's a great deal of difference in the dispersal or the colonization potential of species from our mainland. Some species might be much better at colonizing than others or immigrating than others. With respect to extinctions now, we might see that extinctions are not entirely independent, which is sort of what we assume in the basic model. One way that might happen is that if we have species that start to get crammed into an island, we get more and more species, we find that competition now becomes intensified. And with that intensification, we might expect to see more species going extinct. So there are some other variations as well. And I would say that an important variation is the effect of isolation now on extinction. So remember that we focused our efforts on isolation in terms of examining how isolation affects immigration rates. But it can also have an influence on extinction as well. Okay, so let's have a little bit more closer look at this variation, and that being the effect that isolation now has on extinction. So remember before, we reckon that isolation really has an effect on immigration, right? So if you're further away, it's very unlikely that you'll actually receive an immigrant. And this is the graph that we left off with when we talked about that, okay? So in this variation, we're assuming that in fact isolation will also now have an effect on extinction. So why would that be? For an island, let's say, that's really close to a mainland, for example, it's quite possible that if a species was just about to go extinct, that it stands a better chance at receiving more individuals from that species from the mainland. In other words, the proximity here allows for those species to reach that island just before that species is about to go extinct. And so, in other words, there is this sort of rescue effect. A species on the verge of going extinct is rescued from extinction by virtue of being closer to a mainland. And so we're going to call this variation the rescue effect variation. So extinction rates are also affected by isolation under this variation. So what would that look like? Well, we would expect for faraway islands extinction rates to be higher than for nearby islands. Again, and the reason for that being that nearby islands stand a better chance of being rescued. A species there about to go extinct stands a better chance of being rescued simply because of this proximity to the mainland. So we can draw a new graph here, a new line rather, to represent that. And what do we see? We see that we have a change now in our species richness. So if we look now at faraway islands, our species richness now is the same as it was before. But on nearby islands, our curves have adjusted a bit, and we would predict now that our equilibrium number of species, so this would be S hat for nearby islands now, will have shifted in this direction. Got it? Easy enough? So that's the rescue effect variation. We would expect more species richness on nearby islands. So let's now have a look at another impact. Let's look at the effect that area now has on rates of immigration. So before we said that area really only affects extinction. And this is the graph that we left off when we were talking about that. But now we're going to assume that area actually has an influence on immigration as well. And so we'll modify this graph a little bit. Why would area impact immigration rates? Well, the basic notion is that larger islands, right, bigger islands stand a better chance at intercepting an immigrant that's headed out to try to find land, right, or to try to find a place to set up. A larger island stands a better chance at catching one of those things relative to a small island. So if you're a little teeny island, you probably won't catch immigrants as well as a giant island. I think that's the underlying notion. And so we call this variation the target effect variation, and I've put TE up here in the corner to indicate that. So it's a target effect. These bigger islands represent bigger targets. So what would that look like graphically? Well, our large island would be represented here, and our immigration rate on smaller islands then would be quite a bit lower because of this target effect. And we could then draw that on our graph. And what do we see with respect to species richness? We see for large islands, our species richness remains the same. Our prediction is the same. But on smaller islands, things are a little bit different. Where do these two lines cross? These two lines cross here. So our S-hat on smaller islands now has shifted in this direction. In other words, on smaller islands we would expect less species richness at equilibrium than larger islands. Fortunately, it's relatively straightforward to incorporate these variations into our model, but we won't cover those here. To wrap up, let me just briefly return to conservation. So remember at the beginning, we talked about habitat fragmentation and how that's really a conservation concern because it takes landscapes and fragments them in many ways into islands. So imagine a clear cut that reduces a big continuous landscape, a big continuous forest, down into a smaller forest, right? What can we expect? What can we expect in terms of species richness, in terms of perhaps biodiversity? Well, clearly that clear cut is going to cause a reduction in the number of species, and that initial reduction, that shrinking of species, you might say, is oftentimes referred to as the term faunal relaxation. So it's kind of a strange term, but it refers to that shrinking of species. Now we know on that island that species richness then, once it's created, will really be a function of immigration rates, of extinction rates, of our potential mainland populations, right? So populations elsewhere in that contiguous forest. And it may also be a function of its size as well as its degree of isolation. And what we hope here is that these basic tenets, right, these basic tenets of island biogeography give us really a framework for better planning and mitigating this type of habitat fragmentation. Let me now quickly just turn to another example, and that is the example of national parks and protected areas here in North America, because we do see island biogeography really being played out. So as you can imagine, we have national parks in North America that were created. They're very well protected, but what we've seen is that areas surrounding national parks, which are not protected, have slowly over time become more and more developed. And so that's created more of an islandizing effect. Now, a researcher looked at this islandizing effect in the context of island biogeography and basically examined mammalian extinctions in 14 national park and national park contexts. So here's a graph of some of those results. So here is a graph that shows that relationship between extinctions and area, right? So here we have the number of post-establishment extinctions. So that's the number of mammal extinctions that has occurred in these 14 national park and national park complexes since their establishment, right? So on the y-axis we've got post-establishment extinctions relative to area here on the x-axis. And all of these little dots represent national park or park complexes. And you can see a pretty striking trend here, right? There's really a negative trend with respect to extinctions relative to area. This line here is like a regression line. So what you see here is that larger parks and larger park complexes, those things that are bigger, have shown fewer extinctions than those parks that are smaller up on the sort of left side of this graph. And not only that, extinctions have outnumbered colonizations in these parks. So this, in some ways, is what we would expect from island biogeography, right? Unfortunately, it seems that only the largest of the national parks are big enough really to maintain an intact group of mammals, an intact mammalian fauna. And not only that, even if we superbly manage these national parks, which I really think we do, by virtue of their size and their isolation, right, which is due to greater amount of development surrounding these parks, we would expect to see a gradual decline in the number of species over time. So perhaps with this knowledge we can shift our frame of reference here and focus a bit more on mitigating this development surrounding these national parks. And by doing so, we essentially reduce that islandizing effect. So island biogeography here gives us a framework for really understanding patterns of species richness, like in national parks, but also a framework for making decisions about how we manage landscapes into the future. So at this point, you should have a good solid understanding of the equilibrium theory of island biogeography, its main concepts, its main ideas and predictions. Not only that, how you can model it, and perhaps more importantly, how it may relate to your own work.